Hi, this is Mr. Coon. We're going to finish off this problem here and find out what the final velocity is. So we're going to find out also the velocity in the y direction, but we're also going to find the final velocity when the ball hits the ground from the Burj Khalifa, 828 meters high, with Ronnie Harbison kicking it on the horizontal at 58.2 meters per second. And of course, considering that air resistance is negligible. We found out also that the time it takes for it to actually travel is 13 seconds. We know the the horizontal component. We know that it's 58.2 meters per second in the horizontal. We need to find out, and we already know intuitively that considering air resistance is negligible in the horizontal, okay, if you notice here, the final velocity is going to be the same as the initial velocity. So there's no acceleration in the horizontal component, considering air resistance is nil, and also that there's no acceleration. So first, let's find out Vy. Vy we can easily find out because we found out how long it takes for the ball to drop actually to the spot. So remember, the time it takes to get across from the horizontal component is the same as the time it takes to get down to the ground. So we can figure that out. So we know, let's put it in orange, that Vy equals let's put it below, equals Uy, and all right, let's put it in plus AT plus AYT. Beautiful. And if we plug in these values here, it should equal, so Uy we know as, because it starts off, so from in the vertical direction, it starts off with the initial velocity of 0. And we add that. So here I'm already going to take it away because remember, in the y direction, our acceleration due to gravity is negative 9.8. So I will already take away 9.8 meters per second. So which makes sense that for every second, it will decelerate, or we should say it will accelerate in a downward position 9.8 meters per second every second. So if we multiply that by the actual time it takes to get down there, which is 13 seconds, we'll actually find our final value for our velocity in the y direction. And that is just negative 9.8 multiplied by 13. Easy. It's going to be negative 127.4 meters per second. So we know that this negative is in the downwards direction. So let's fill it in here. We won't need to fill it in, we've got it here. So in the y direction, at the very, very final, it's going to be going at 127.4 meters per second. So logically, we can do vector addition again. So we can use a bit of our trigonometry. So just to remind you, if you've forgotten your trigonometry, that, sorry, not trigonometry, I apologize. If you have forgotten your Pythagorean theorem, sorry, is a squared being, with a squared being the resultant, equals b squared plus c squared, with b and c being the components in your function. So we know that the downwards, okay, the vertical, okay, the vertical velocity is going to be 127.4 meters per second. And we know from up top, let's have a look up top, that our final velocity in the x direction is 58.2, because remember, there's no acceleration. So in the x component, in the horizontal component, the velocity is going to stay fairly constant. And let's do that more in actual scale. It's going to be more like this, really. So it's 50. Let's have a look. Again, Mr. Coombs already forgotten it. 58.2 meters per second. 58.2 meters per second. Beautiful. So our resultant vector, and I'm going to put that in green. Our resultant vector is going to be to the bottom right. Okay, so our resultant is going to be something. So to figure out our resultant is going to be A, it will be the square root of B squared plus C squared. So our actual components. So if we put in our components, it's going to be the square root, it's going to be a little bit longer, of 127.4 squared plus 58.2 squared, which is going to be, let's put that in yellow. Okay, let's clear this. Square root of 127.4 squared plus 58.2 squared equals, it should equal 139.70 exactly, almost exactly, but with a few more decimal places, meters per second. Now same again that we did with the actual with the displacement, we want to find out what it is to the horizontal. So when we're comparing its origin to its final. So, and what we found out something in the last video, that this angle theta is going to be same as this angle theta. Okay, so they're the same thing. So let's do theta I and theta, say, j. So we found out in the last video that theta I is the same as theta j. So we can even just solve for this theta here. So let's do that. Let's use our very basic trig functions in order to actually solve that. So just to remind you, our trig functions are oops, that looks like an L. So and let's just use TOR, because we're going to use what we had before. So you could have figured this out without even knowing the resultant, given you have your actual components. So we know that tan theta equals our opposite, which is 127.4 over 58.2, which is our adjacent component to the angle. So if we get the inverse tan of each of those sides, we get theta equals inverse tan of 127.4 over 58.2, which is, so inverse tan of 127.4 divided by 58.2 should give us an angle of 65.45. Oops, 65.45 degrees. So our very final velocity, so just to finish this off, let's put it in green, so it's final. Our final velocity, VF, so our very final velocity is 139.70 meters per second at 65.45 degrees to the horizontal. So we've solved it. We've got all our information now. So I hope that was useful. And in our next video, we're going to be talking about one more different type of motion. So where it's a full parabolic motion, just like in Angry Birds. So hopefully that was helpful, and I'll speak to you guys in the next video.